Hello, everyone. Welcome to ING's Data Science Meetup. My name is Nicole Bozica, and I'm the communication expert of ING's Wholesale.
Hello, everyone. Welcome to ING's Data Science Meetup.
And welcome to my co-host of today also, Vaidotas Koulianskas.
Thanks, Nicole. Hi, everyone. My name is Vaidas. I'm a chapter lead of Data Science at Digital and Customer Interactions Tribe here at ING. Very happy to be here today and looking forward to the event. Let's get started.
Me too, Vaidas. So let's kick off with our first talk and have a sneak peek to the background of our first three speakers, all coming from ING's Risk and Pricing Advanced Analytics team. So we will see Dan Timbrell, who is a data scientist, moved 3 years ago from the UK, and since then he's with ING, working on a variety of projects, currently focused on automated income detection. We will see Sandro, a data scientist also with ING for the past 4.5 years, and mostly involved in credit risk models. And last but not least, Tim Vink, the lead of ING's Risk and Pricing Advanced Analytics team. Tim is data literate and a digital native, and he's building machine learning models at ING since 2014, which is quite a long time. And today they will talk about Scorecard and how to make logistic regressions great again. The floor is yours, guys. Good luck.
Yeah, thank you all. I assume you are able to see my screen. If not, please tell me. So yeah, today me, Tim, and Dan are gonna talk about Scorecard. It's a very cool open source package that we just released. So I'm very excited to talk about this with my colleagues. Before we start, just a quick introduction who we are. Basically, we are the Risk and Pricing Advanced Analytics, and as the name suggests, we are responsible for development of machine learning models for the risk and the pricing domain. The team consists of roughly 15 people. It's very international. If I did not miscount, I think we have 9 different nationalities and very multiple backgrounds. So we have people from computer science, engineering, physics in the team. Now, we are focused mostly on machine learning models, but now and then we encounter also what we tend to call traditional models that are scorecard models. And at the end, you will see why also we decided to kind of develop this package and open source it for you. Now, before we move, let me give a quick introduction what Scorecard is about. So basically, scorecards are the way how risk models, how loan decisions were being taken for quite some time in the bank. And this dates back to, let's say, the late 80s. And back at the time, you pretty much have something like you see on the left. You have actually a scorecard. So you will have some variables here. You will have some, let's say, reference fields, reference buckets. And for every bucket, a customer will get an amount of points. In that case, assume we have John. John is 31 years old, falls in this range. This means we'll get 25 points. Based on his income, he will get 28. There are multiple steps. He gets a final total score, in this case of 238. This number means nothing, but also means a lot. And basically, if this score is above a given threshold, the loan is approved. That's how it worked. However, back at the time, there was no real modeling or optimization, how these buckets were defined, and the points was really like the bankers playing behind and based on some business knowledge or so on. How did we evolve since the 80s? That's almost 30 years. Well, actually, scorecards are still quite used in banking. However, they're slightly different. And what really changed is the way how we develop them. So feature selection is normally done, and the way how we define the bucket, these are optimized steps. So I'm going to see a bit later. The way how we assign the point, is the optimization. And basically, the final sum of the points is linked to a probability of default. Now, how we are building this, you're basically having different values of points for different features. You sum them linearly. You're in a binary classification setting, so pretty much you're trying to predict if the customer might default or not. And linear combinations and binary classification usually call for a logistic regression. However, these tricks to basically define these buckets and how you assign these points, you will see actually that they make a simple logistic regression model way, way powerful, and that's also what Scorecard includes. However, in a traditional kind of process, developing this is a lot of manual work and usually lies outside the data science workflow. What I mean here is that, as a data scientist, when you enter into this, you suddenly have to deal with a lot of Excel sheets with different type of software that you're not used to, and this is not very convenient, at least from a data science perspective. So that's why we decided to build Scorecard. What is Scorecard? It's an open source package, and basically it provides a toolkit to build Scorecard models in a scikit-learn compatible API. Note that the K in Scorecard is not a typo, as K relates to scikit-learn. That's why it's like this. And what problem does it solve? Well, the two main problems I mentioned. Automates part of the tedious part of building these traditional models, and integrates nicely in a data science workflow in Python. Before I move on, just to give an idea how well this performs. So normal Scorecard models, they're going to outperform any logistic regression. And in general, they're going to be performing always worse, but can get very close to, let's say, 3 ensemble models like XGBoost or IGBM or so on. And there are actually some fundamental reasons why this is happening. Here, I just try on a dummy data set, and you can see actually the results. If you look at the ROC AUC of this model, you will have the logistic regression scoring around 0.65, the Skorecard at 0.76, and the random forest at 0.77. So it's getting pretty close. Now you should ask, like, why should I actually care about this? Well, because what this is implementing, there are a few simple tricks that are known for a long time in the creators domain, but they're not usually known in the data science community, that can actually boost logistic regression performance. This can, if you use Scorecard, you can develop quickly a baseline model that is a very, very simple model, and you can use it as a baseline for any machine learning that might outperform this. It's damn easy to implement. As you've seen, actually, at the end, you're going to end up in kind of something that you can implement even on a paper sheet. And in addition, there are quite some nice reusable components that can be reused in your ML workflows. Just to give you an idea, 2 slides on the theory behind Scorecards. Basically, there are 3 main steps. You can already guess what they are. There is the variable discretization. This is the bucketing. This is the part that is done univariately and is very, very intense manually to develop, and that's where most of the automation comes in. There is the part of the encoding. Basically, this is explained on the next slide, especially the weight of evidence encoding, like what it does. And at the end, once you do these 2 steps, you're basically building a logistic regression on top of this. Note that these steps are nothing else than scikit-learn transformers. You put it in a model, you get a scikit-learn pipeline. It works amazingly well within this context. Now, why do they outperform traditional models? Basically, what this kind of bucketing trick does, it kind of deals with nonlinearity. Now, assume that you have a feature X1 here. This feature X1 has this type of relationship with your target. Here, I'm talking about the log odds, because that's what is the linear component of the logistic regression. Once you discretize them, so let's say you define 4 buckets, basically you're compressing information and you're destroying this nonlinear relationship. And then you can do any type of encoding, but the weight of evidence encoding has this very nice property that if you transform, basically the weight of evidence is nothing else than looking at the fraction of target 0 over target 1, taking the log of those for each bucket. This is what you compute. And the nice property it has that is linear in the log odds. And actually this can be proved very, very easily. What does this mean? That basically now, if you transform the weight of evidence and you fit it into the logistic regression, you have a linear thing that the logistic regression is going to manage very well, and that's where the performance boost actually is coming from. There's nothing more than that under the hood. Now, just to get a parallel with 3 ensembles, actually 3 ensembles are very, very similar under the hood to Scorecard models. And what I mean here is that 3 ensemble kind of performs the bucketing in a sense that when you build a single tree, the tree algorithm, kind of every leaf can be matched to a bucket. There is the major difference, and that's where ensembles actually gain their biggest performance boost, is that they treat interactions while Scorecard model don't. Then when you encode, basically you're basically mapping every leaf value to a number, depending per algorithm. And then at the end, you do some sort of linear combination, which is Scorecard models is fitting logistic regression. In 3 assembles, you basically combine weak learners into strong learner. Now the Scorecard actually implements kind of univariate bucketers, and that's going to be the 3-decision bucketer that kind of runs this thing univariately. So if you basically build a random forest with 1 feature per tree, you're basically building a Scorecard under the hood. And this is really, really quickly the theory behind Scorecards. And now I will leave the floor to my colleague, Dan, who is going to give you a demo to see how these bucketers actually work.
Yeah, exactly. Hey, hopefully you can hear me. If not, then just give me a quick shout. And yeah, you should be able to see my screen as well. So I'm just going to take you through, as Sandra said, a basic overview of what we already have in the Scorecard package, implementing all of the theory that Sandra really nicely just covered. So first, what we're going to do is just load a really simple data set that just contains 2 variables of each type, so 2 numerical and 2 categorical variables, which you can see here. So education and marriage being the categoricals, the limit balance and the bill amount just being the numerical ones. So bucketing with Scorecard, we're first just going to take a look at a really simple bucketer just to show you all of the main aspects that come along with the different bucketers that we have. And then I'll show you the more sort of, let's say, exotic bucketers that we have inside this. So let's just start with the equal width bucketer. Now, the way that this works is that imagine you have, let's say, a variable where you can see it distributed here along the x-axis. Well, essentially what this, what we might want to do is to bucket this here, a continuous variable, into some buckets of equal width. So here we essentially have, we want to bucket this essentially, in this case, 4 times. Each one here has the same width as the previous one, so pretty straightforward stuff. So here, what is contained in the buckets will be different number of instances. But let's say that we want to implement just this equal width bucketer. Well, it's really easy to do. We firstly import from Scorecard bucketers our equal width bucketer, and we want to go ahead and just fit and transform this immediately on our data. So we have our X and Y data. Notice that we firstly specify the number of bins that we want to put the data into, so in this case 4, and we want to go ahead and pick name the variables that we want to put into this bucket. So in this case, we're doing both of the numerical variables that we have, and so you just specify these variables as a list. You go ahead, fit, transform, and you can see now that essentially what has happened is that the limit balance and the bill amounts, which previously had lots of numerical variables, are now essentially just put into these buckets, a maximum of 4 buckets each. And you can see when we look at, for example, the limit balance unique, there are indeed 4 unique values. So that's pretty straightforward. The really cool thing about the Scorecard package is that we can implement it, it's compatible with scikit-learn. So immediately what you can see here is if we put it into a pipeline, for instance, scikit-learn pipeline, where we take our equal width bucketer, but then take other pieces from scikit-learn, such as the one-hot encoder and a random forest classifier, we can immediately just create a pipeline from this, fit, predict, and there's no issues with this whatsoever. So this is really cool. Some of the aspects that belong to all of the bucketers, I'll show you now. So for instance, after we've fitted our bucketers, what we can see, for instance, is a bucket table. So here we create a bucket table per feature. So what we have here is the bucket table for the limit balance. And we can see that essentially what we did was we specified give us 4 buckets. And we do indeed see 4 buckets here, 0, 1, 2, 3. We also have a special bucket for the missing values. In this case, we don't have any missing values, so it's just 0 counts. But you can see the labels, so the boundaries that are provided by the bucketer for each of these, and the counts and the percentage of counts inside these buckets. So pretty straightforward, but very nice to see, just to be able to see a more granular overview of what the bucketers are doing. Now, often when it comes to bucketing your values, what you want to do is you want to take some special values and put them in their own buckets. These special values might mean something, let's say, more than normal than your other variables, or than your other values, sorry. And we can very easily implement this inside our bucketers. So for instance, if the value of 50,000 in our limit balance meant something unusual and we want that in its own bucket, we can very easily do that. Similarly, if we want to bucket anything between 20,000 and 30,000, for instance, in its own bucket, we can easily do this. We firstly just define a specials dictionary. Again, we want to look at 4 bins here. We say, look at the limit balance, pass through the specials, and pass through the remainder. Now, this remainder essentially means that any variables that we do not specify here, we can just we leave them untouched as they are like this. So the bill amount, for instance, has not been touched here. We can also drop a lot of the variables, so it only transforms the variable that we specify here, but in this case, I haven't done that. We can also specify here a missing value treatment. So often you might want to put your missing values into their own buckets. You might want to put them into the most common bucket or the bucket with the most instances of class 1, for instance. And we can specify that here. So in this instance, what we do with the missing treatment dictionary is we say any missing values in the limit balance, put them into bucket number 2. And you can see here, for instance, this is indeed the case. So we have bucket number 2 here, and we see that firstly we have this boundary, but also the missing values exist in here as well. So that's really nice. The default value is to just put the missing values into their own bucket. We can now begin to plot all of the underlying data. So this essentially, this bucket table here, we can begin to plot this into its own nice little bar plot here, just showing the nice visualization of exactly what it is that we've been putting into this bucket table. So you can see here, for instance, there's more counts inside this bucket here than the others. And you can see if I hover over it, it's a nice interactive plot. So that is really nice. So let me just take you through briefly before I pass on to Tim and Fink, the different buckets that exist inside this package that we've created. So in a similar vein to the equal width bucket, we have an equal frequency one. So in this case, instead of saying that we want to have equal widths of buckets, now we want to have an equal number of counts per bucket. And this is, you can see here, for instance, if we had this variable, then this would be a smaller bucket because you're capturing so many instances. And as you get further and further away from this mass here, you would need buckets that get wider and wider. So this next bucket would be really, really wide. We have an agglomerative clustering bucket. So this is if you have, for example, main sort of points of mass inside your data. So imagine you've got your data distributed here where you've got 3 main points of mass. It essentially just uses the agglomerative clustering that exists within scikit-learn to essentially just bucket these. Again, very easy to just import this bucket and immediately invoke it in the method that I showed previously. The nice thing here is that so far I've just showed you what to do with numerical variables, but we do have cases where you can essentially manipulate the categorical variables, and we do that, for instance, with this ordinal categorical bucket. So here you can, for instance, have it where now your categorical variable gets bucketed in a way such as the most popular, the most common instance of this category gets put into bucket 0, the second most bucket 1, 2, 3, and so on. Now I want to talk about the supervised bucketing that we have. So before, everything that I showed was just unsupervised. It doesn't need to see the target that we have that goes along with this. There are some now more sophisticated bucketers that I can show you. A shout out should go out to the opt binning package. So here they put in some really nice monotonicity constraints, for example, when it comes to the class 1 and some extra things like this. So definitely worth checking out if you want to get more involved into, let's say, scorecard specifics. And the way that we can essentially implement this, you see now I'm essentially implementing a fit transform with both X and Y. So it's using the target to generate the buckets for this limit balance. And here we don't even need to specify the number of buckets. It tries to figure out the optimal number of buckets here. And so you can see here, for example, bucket 8, bucket 3, and so on. So this is automatically being bucketed. Putting all of this together that I've just shown really briefly, what you can see is that in a more sophisticated approach, what we would have is the variable specified, the variable type, so categorical in this instance, the maximum number of bins that we wish to see for a particular variable, how we want to specify, how to treat missing values, and the minimum size per bin. So here, at least 5% of the instances must be present in a bucket for it to become a bucket. Otherwise, there will be no bucket. So this, in the end, is when you want to start getting more and more sophisticated. You'll add more and more, let's say, parameters into this. We also, furthermore, have a decision tree bucket. So here, essentially just using the decision tree algorithm from scikit-learn to, again, pick the sort of optimal number of buckets that we want. So in this case, the limit balance. So this is really cool. After this, again, we can go ahead and plot the bucket table. In this instance, what we see now is a really nice, sophisticated granularity of what exists inside this bucket. So the label that exists for each one. So we've declared some specials, for example, for 50,000. This gets its own special bucket, -3. This other special for -4, the bucket for missing values, and the 10 remaining bins that have been decided. How many of the class 1 exist in this bucket, how many class 0, and so on, known as the event rate here. This is the percentage. The weight of evidence and the information value also provided. And again, what you can see now when you plot the plot this bucket that we have, it also gives the event rates. If you're plotting, for example, defaults, this would be the default rate. And you can see this sort of organized via the event rate here. So this is really, really nice. If you want to dive a little bit more into the granularity of what exactly the bucket is doing under the hood, well, you can look at the features bucket mapping. So here what you can see essentially is the name of the feature, the type, and so on. But I think a really cool thing, just to demonstrate before I now pass on to Tim, is the fact that you can save these buckets that you generate into an output. So for example, here we're saving this decision tree bucket into an output YAML, and it looks something like this. So it will save the name of the feature, the values that go along with each of the buckets, and the specials, things like this. But the really cool thing is that then we can create another bucketer from this file. So here what you can see is that I load this output and immediately create a bucketer. So for instance, let's say I change this value, I put in 99999 here and save this. I can now immediately load this bucketer, and what you see when I look at the bucket mapping is that this is indeed automatically just been implemented. So in a nutshell, that is all of the functionality that exists right now in the Scorecard package, and I will pass over to Tim Fink.
All right, thanks Dan, thanks Sandra. So we've covered the theory, we've covered the bucketers, and it's time to put everything together. There is, however, one more problem, and that's the fact that in practice, we usually take a two-step approach to bucketing. So there is the raw values, then you do some pre-bucketing into about 50 to 100 buckets, and then you start fine-tuning it into, let's say, 5 to 10 buckets. And the reason for that is to make the optimization problem from there to there a little bit simpler. It also makes it easier to incorporate domain knowledge from experts, and also makes it easier to tweak a little bit with constraints on your bucketing. For example, in monotonicity, that the event rate per bucket is either decreasing or increasing. So for that, we've made a special type of bucketer called the, so this also doesn't work. So a sequential pipeline, where you just bucket it twice. The problem is the special values are not propagated. The bucket mapping from the raw value to final bucket that Dan just showed also doesn't work if you do it in 2 steps. And the inspection with the bucket tables is also not easy to inspect. So we made a special bucketer called the bucketing process. And it looks like a lot of code, but it's not that bad. Basically, you now have 2 pipelines, one here and one here. There's the pre-bucketing one, where you bucket any features that you want. And there's the final bucketing. And you can specify the specials as well. And then you have a bucketing process. And this will take care of all the bucketing. And this bucketing process works the same as any bucketer. So let me show you. This is the same bucketing process, but then with some data loaded. I have a data set, and I take this bucketing process over here, fit transform it, and now it's bucketed, and I can use exactly the same methods as Dan described. So this, for example, a summary, and now you see the number of pre-buckets, that's new, and the number of final buckets, from 14 to 10, from 15 to 7. You can also inspect the pre-bucket table for a feature. We have 12 buckets here, and then the bucket table. and the same for the pre-bucket table plot and the bucket plot. And you can do the same trick. So if you want to get the raw buckets in a YAML file, this bucketing process will do all the math to get the transformation from raw data to final bucket. And that's basically what we need to put everything together. So to build our final scorecard pipeline, quick recap of the theory from Sandro. We bucket our features over here. We apply weight of evidence encoding, and then we build a logistic regression. So in code, that looks like our bucketing process over here. A weight of evidence encoder that we also implemented in Scorecard. A column selector in case you want to select some features, and the logistic regression. We have a variant from Scorecard that's only there to show some extra stats. And again, this weight of evidence encoder, that's just translates a bucket number to the log of the event ratio, or let's say the default rate or the bad rate of each bucket. And that's it actually, except this pipeline is bit verbose. It's very common. So we also implemented the scorecard class. So this over here is what you would use in practice. Your model is a scorecard where you supply a bucketing process and then you can fit it. And that looks like this. So that's it. And this is you have a get stats method. So you see all the features in your model, and you can access the bucketing through model.bucketing, and you can do all the same stuff as we've shown before. Like Sandro said, it's a really good baseline. So you could just also call Scorecard without any parameters. It will use the default bucketing process, and it will auto-detect the categoricals. So this is everything you need to do to use Scorecard as a baseline. You can see the AOC of a Scorecard model and compare it to something else in your problem. So to conclude, so that's a really fast conclusion. Scorecard is open source. It offers reusable scikit-learn components that are also applicable outside of credit risk. It offers a really good baseline, so don't check it out. And it's compatible with a lot of other scikit-learn compatible tools. And we have some really cool plans for the future, including interactive dash apps to do some manual bucketing. We'd love it for you guys to be involved, so go check it out on Scorecard. Let us know what you think. Open some issues if you find find some bugs or have some ideas. I think we might have a little bit of time left for Q&A. So thanks. You're on mute, Fayez.
Hey, yeah, I was muted. Thank you very much, guys. Cool demo, nice presentation. Indeed, we have a couple of minutes for the Q&A of 1 or 2 questions. Let me see what we have in the comment section. So one question for you is Francisco is asking, what happens when you can't find a univariate correlation? Could you do bucketing based on 2 features?
Yeah, I can maybe answer this. Basically, if you don't have any univariate correlation, this in other words means that the feature is not predictive. So like in any machine learning model, you have maybe the feature importance will be very low, you will drop it. That's it. And you will try to find some features that simply are predictive. Yeah, there in the docs, there is directly some tutorials how to run feature selection in this context. We couldn't really cover everything because of time constraints, but actually there is a kind of best practice to run feature selection also with this type of models.
Yeah, very nice. And someone asked for a link or whether it's open source. So it's very good that you shared the link. I would encourage others to try it out, try it for themselves, run the notebooks, see if you can add or see some value there. Let's pick up one more question. Armando is asking, does Scorecard allow for non-monotonic bucketing? In case from a modeling perspective, you wouldn't necessarily want to impose a monotonic relationship.
Yeah, I can answer this one as well. So basically monotonicity is a very nice to have, but indeed is not a must. This is more for how you're going to interpret the model and the relationships. Now, all the bucketers by default, they don't really have any monotonic constraints. They're going to optimize the splits, like let's say a 3-decision bucketer is going to optimize to maximize the entropy, for example, or the Gini. Hence, there is not necessarily constraint on monotonicity. The only one that really has a monotonicity is the optimal bucketer, which actually takes over from odd binning from this package from Guillermo. So we are basically using this to impose some monotonicity. And if you do the bucketing process by default, you are looking for monotonicity. And this is kind of a good standard because, yeah, it's more interpretable, but indeed is not a strong requirement for the model to work. I hope this answers the question. Yeah.
Makes sense. All right, I think we ran out of time. Thank you very much, guys. Again, thanks for the answers. And for everyone, go out, check out the package, and yeah.
Thanks.
Let's move on to the next.
Very nice presentation. Thanks, Vidas. So let's move on to our next speaker, Ilan Friedman Rojas. Ilan was once a theoretical physicist who then moved on to work to data science. He completed 2 research fellowships based on hybrid industry-academia collaborations with the University of Leeds and the University of Essex. And later on, he joined ING, and he is now a chapter lead data scientist within WBAA, so proud to call him my colleague. And today he will talk about time-to-event analysis, a pedestrian approach. So passing the mic to you, Ilan, good luck.
Can everyone see my screen? I hope so. If not, someone will tell me. Okay, so good afternoon. I'm going to tell you a bit about the time-to-event analysis, and it links a bit to the talk from my previous talk from my colleagues, in that they were concerned in kind of like if something will happen and how to evaluate risk in that context. Here we will kind of be considering the question of when, right? So, oh, by the way, there's a little bit too much text in the slides. Don't try to read it all. You can it's just to make them stand alone for later. But just listen to what I'm saying, and then I'll talk you through them anyways. So say you have a scenario where you're asked to predict how far into the future a certain event will occur. And the event can be anything. They can be, in the context of banking, could be a default, a loan application. In the medical context, it could be a death, an asthma attack, a stroke. It could be anything really. This framework is completely general. And say you have some relevant historical data on these events, so kind of their timings. And you also know some of the characteristics of the entities, right? So whether that's a client applying for a loan or that's a person who's unfortunately at risk of a stroke. So how would you approach this, right? And I'll give you a second or two to think about it while I switch slide. But there's basically 2 default approaches that you could go into kind of off the top of your head. And one of them is to say, all right, the target variable, which is time to event, is continuous. So this is a regression problem. I'm going to fit a standard regressor to it. Another way to do it is to say, all right, actually, I'm going to impose a time window. And I'm going to say this is a classification problem where if an event happens within the window, it's a 1. If it happens outside the window or not at all, then it's a 0. All right, and you could try to do that. And I'm going to argue that both of these approaches have downsides. And I'm going to propose a very well-known and, yeah, by now very mature solution. But okay, so I'll give you a brief overview of some of the drawbacks of these approaches. So if you decide to go for the regressor, then if you read the first line there, you can end up with predictions like, okay, if you were trying to predict loan applications, we can expect the loan application from this company in 1.246 years time. Yeah, that's not really a credible prediction, right? It's I mean, you can make it, but when the time comes, let's see if that actually happens, right? It's very unlikely unless the process is already very deterministic, in which case you don't need to model it like this. And also keep in mind, if you're training a regressor to time to event, then what do you do with the companies that say haven't applied for a loan yet? So there is no target variable there, right? They might apply later, but they haven't yet. And so there, are you going to drop them? But that presents other issues as well, right? Because you can do that in a training set, but in a test set, you wouldn't know in advance which ones are or aren't going to apply for a loan. So really, you can start to see that the whole scenario is a bit strained already. And if you go down the classifier route, then you can say, all right, what's the correct time window to use? And you can say, due to business reasons, it's this. but still, you're imposing a cutoff, right? If the event happens just outside the window, you pretend that it didn't happen at all, and so it's not really ideal. And within the window, you kind of say yes or no, but there's no measured probability, right? Of whether how sure you are that there will be an event. So things. Oh yeah, and there's further drawbacks, which is that both of these approaches would neglect something which is very crucial to these problems in general, which is time at risk, right? So for example, the complete hypothetical here, by the way, this whole talk is about kind of toy problems and hypotheticals. Don't read into it because you'll just get false readings. But if say you're talking about probability of default, right? Say. And then, so you're not equally likely to default the day after the loan was granted as you are probably a year later, right? Or 2 years later, or 3 years later. So the time at risk, when you're at risk is when you have the loan, right? When you're given the loan, you become at risk, and the event of interest is, say, a default. So the time at risk is really a crucial predictor, right? You expect things to evolve over time, and the time, the relevant time year is at risk, is time at risk. So that's another issue. And with a regressor, keep in mind as well, you could accidentally predict far outside of the data that you actually have. So quick example, but for example, with with COVID, it looks like a good fraction of the medical profession even was a bit surprised by people having long-term symptoms, right? So you shouldn't really, if you only have follow-up time of a certain amount, you shouldn't really predict outside of that. But a regressor, if you give it the right inputs, will predict anything, right? Completely outside of the data you have. You don't want that. And these are all signs that the tools are not really fully fit for purpose, okay? So I'll make the case that due to all these reasons, treating it as a standard classification or regression problem is a bit of an issue. So going through the points quickly, what do we actually want? Point predictions like 1.246 are not really an option. We want to predict probabilities. Time dependence, we want to model that smoothly. We want to account for time at risk. We don't want to extrapolate, we don't want to have predictions outside of the region where we actually have data over. And causality must be respected at all times. So if you start conditioning on outcomes, so saying dropping the ones that haven't gotten the loan yet, well, you wouldn't know that at the beginning, so you probably shouldn't be doing that. So these are the desired kind of modeling characteristics, and there are very well-known models that kind of fulfill all these things and fix all the problems that I just posited to you. So this is a very well-known and studied problem, and medical trials, I'll give you an example in a second, rely heavily on this, and it's generally called survival analysis, time to event analysis, different names, it's the same techniques. And just for clarity, I'll frame everything from here on is where the event of interest is death, right? I have no medical background, I'm not an epidemiologist, do not read anything medical into this. This is purely as a toy problem, so you can see how you could apply it to the case that you're interested in, okay? So the simplest thing you can possibly do is to use life tables, where you literally count within this period of time, this many people died, and this many people were at risk at the beginning of the year, right? And Bernoulli started doing this in the 18th century, I believe, and they're still in use today. So if you look at the table at the bottom right, that's from the Office for National Statistics, and you'll see the column age, which is X, and you'll see a column called QX, which is explained on the left. But it's basically the mortality rate between time X and X plus 1, right? So it's the fraction of people who died in between that age and the next one, divided by the people who were alive at the beginning, right, of that period, using data from 2017 to 2019. So these are kind of good points to anchor your analysis on, and this is how you can start to calculate probabilities given event data, okay? And you can formalize this a little bit more, and you can say, right, there's this thing called the Kaplan-Meier estimator. I'll explain what the equation is. So basically, if I is a given time, so in the previous table, that would have been an age, and lowercase t is a time that you're considering at the moment. So you want to say, what's the survival rate up to, 30 years old or something like that. And then di is the number of events you have at time I, and ni is the number of people who were at risk at the beginning of time I. So this is the proportion of people who had an event in time I, and 1 minus that is a proportion who survived, right? And if you multiply this factor over all the times that came before it, you basically get the overall survival rate. So if you 0.9 and 0.98 and you multiply those together to see what fraction would have survived by the end, okay? And this actually, it sounds incredibly simple, and it is, but it actually incorporates all the right things. So for example, the time at risk thing that we were mentioning, if you were at risk, you should be counted within the denominator in this n sub I, which means that it correctly includes all the people it should include. Because if you don't include if you were at risk and you're not included here, you're going to overestimate the probability of the event, and the other way around. Okay, so if you do this carefully enough, it's deceptively simple, but it actually should estimate the probabilities well, which if you do in other ways, you will get wrong in the way that I just mentioned, if you don't count the right people in. We assume non-informative censoring. I won't say much about that, but basically, you can think of it just to give you an idea of kind of how complicated these processes can be and why they're so tricky to get right. If you like, there's a process driving the event, in this case, death. But there's also, for example, other processes that could drive censoring. And censoring is when someone either makes it to the end of the trial and didn't have an event, or drops out of the trial, for example, because they move city and they stop going to the clinic, right? And there could potentially be that process could also be correlated to some of the covariates of the people, right, involved. And if that could completely affect the events you see and the ones you don't see. So it introduces a selection bias. So in general, it's a common assumption. You can deal with it if you suspect it's not true, but you kind of assume that the censoring is not informative. This is an example, again, taken from a preprint some months ago. I'm including it just because it's topical, just to see that these tools are used, but do not run away with any medical message out of here, because I'm completely not qualified. This is just to show you how these tools are used. So adult patients, the time zero here is when adult patients come in into an intensive care unit. And then at that point, they're randomized to either receive this treatment, the one that begins with a T, the one that begins with an S, or they receive the standard care, right, and control. And what you're looking at here, this is the Kaplan-Meier curves, right? So if you look at the red curve, that's the control group. And it starts at 1, so everyone's alive at the beginning. And then every time it dips down, that means that someone unfortunately passed away at that point. And the tick marks means that someone's been censored, someone dropped out, okay? And at the bottom, you can see the number at risk. That's how crucial this kind of statistic is in survival analysis, that you usually want to include it. And it's important because, for example, here you could see that the middle treatment, the one with an S, actually has quite low numbers. So I wouldn't bet much that that line is statistically different from any of the other two. Okay, so this is the way these things can be assessed, but keep in mind you could do exactly the same thing for any other event that you're interested in, right? These tools are perfectly general. And just as a bit of good news, that a few months later, there's even bigger randomized trials seem to show that one of those treatments, the one that begins with a T, was for certain patients actually effective. And you can see these plots should start to look familiar to you. This is kind of 1 minus the one we were looking at before. But yeah, this is just to make the case that these tools are general and they're heavily used in the medical context. And it's for good reason, because they get a lot of things right, which are actually hard to get right otherwise. Okay, and one of the most common tools is actually Cox regression. And so I'll just walk you through it very quickly, because just in case you see it later, so you can kind of see how it works under the hood. So say you have a general measure of risk called hazard, and it's obviously going to be a function of time, and it's going to be a function also of covariates, right? So the Kaplan-Meier didn't include any covariates. We just said, what's the aggregate over, and you could plot it for different categories and see how they compare, but you didn't include covariates beyond that, right? And that's for categoricals. What if you have something continuous? So here you can include covariates, and this measure of risk has to be non-negative, right? If you're not at risk, then it's 0, and if you are at risk, then it's positive, but it doesn't make sense for it to be negative. And we want it to be mathematically tractable. Otherwise, this is kind of a black box, which we're trying to avoid, right? If you want to do some well-understood statistical inference, then the simpler the estimator, the better, right? Okay, so the exponential function is kind of satisfies both of those requirements, right? It's strictly non-positive, and it's kind of mathematically simple. So we say the hazard function is the exponential of this other function f, which we don't know yet. And now we're going to make some more assumptions so we can actually come up with a mathematical form of something we can fit. And we're going to say, all right, you know what? The dependence on the covariates and on the time, we're going to split it. And inside the exponential, it's additive. At the hazard level, it's actually multiplicative, as you can see here. So the hazard breaks down into a product of it depends only on the time and only on the covariate. And now let's make a further assumption and say that the dependence on the covariates is purely linear. Okay, simplest possible thing you can do. And we're also going to relabel this, the exponent of the exponential of L of t, the time dependence, into H0 of t, which is called the baseline hazard. This is a model proposed by Sir David Cox in 1972. And this is the standard workhorse in survival analysis. There are many kind of improvements to it over the years, etc. But yeah, this is kind of just so you understand. These are the sort of assumptions, and then you can, it's not a linear regression, but you can see where the betas are. You can see that you're going to fit some time dependence, and you're going to fit the betas. So it's just to give you an idea of what this would look like. And using this, you can predict survival probabilities. I won't tell you how because I don't have the time, unfortunately, but you can look it up. And just to say, the way I presented in the previous slide, it looked very kind of ad hoc. I kind of just waved my hands around and made some arguments and came up with a form. But you can also motivate this from kind of a more rigorous mathematical arguments that are based in counting process theory. So yeah, if you're interested, you can go to this paper, for example. One thing that I will say, just because it's kind of crucial if you're going to use these things, is they have an assumption, which is that they're proportional hazard models. And it's both a feature and a bug. The bug is that if this assumption doesn't hold, then the model is not really appropriate. The feature is that if it approximately holds, then it gives you something very interpretable. I'll show you what. So if you consider the hazard of two different people with covariates xi and xj, and you just take the ratio, what you'll notice is that the time dependence doesn't actually have any dependence on the person, right, on xi or j. So that cancels. And this will be crucial for something that I'll show you in the next slide, but it basically, you can get an exponential of beta, which you can then interpret, and that's called a hazard ratio. And you can directly read from it whether, for example, if X was a treatment, and this is actually the same person, and you just consider kind of the same person with treatment or the same person without treatment, then this would give you exponential of beta, because this is 1. And that would give you an indication of whether if this is greater than 1, then the treatment is actually harming, it's increasing risk. If it's less than 1, it gives you an improvement. And if, say, you got x beta equal to 0.6, then that's where you get the headlines in the news saying that this treatment reduces the risk by 40%. Okay, and it's kind of true, but it's also, you got to be careful how you interpret hazard ratios. But yeah, the point here is that the time dependence canceled out, so that the hazard between two people is actually the same. The ratio between them is the same overall time. They're proportional. And actually, speaking of logistic regression, like the previous talk, if this looks too alien to you, then if you take a logarithm here on the left, then you get log of hi over hj equals x beta, essentially. And that looks a lot like a logistic regression, right? Where it would be log of p over 1 minus p, the odds. So you can think of it as kind of similar in that regard. And yeah, as I was saying before, this hazard ratio is just the ratio of two hazard functions, and I'll show you in a second how this actually looks. But if the hazard ratio is bigger than 1, then clearly, okay, if you multiply it h by h of tx on both sides, then you can see that if this is bigger than 1, then the hazard actually went up, right? When you increase this covariate, and this covariate could be, for example, it's 0 here, no treatment, and it's 0 here, plus 1, so it's 1, so treatment. So yeah, if the hazard ratio is bigger than 1, then you increase the risk. If it's lower than 1, then it lowered it. And from the Kaplan-Meier, you can also do a log rank test to see if you can reject the null hypothesis that the curves that you observed were drawn from the same survival function or not, right? So yeah, so hopefully the previous example where we saw the low statistics, hopefully it would fail to reject, for example, but although that was comparison between 3, and you would have to pre-specify everything, of course. Anyways, but that's, I'll leave the details to you. I'll show you how this actually looks like, because when you first look at a survival analysis data set, it looks quite different. So if these were, say, loan applications, or, well, okay, let's stick to that. So I said I was going to stick to that. So so this would be kind of the time of death and the covariates that you might get the data in that form to begin with. But you have to transform this where DI is this indicator variable, where you set it to 0 if they were censored. So if the trial ended and they were still alive, thankfully, or if they dropped out of the trial, so you didn't observe the final outcome. And TI is the time at which that happened. So and XI is our usual covariate. So to show you more kind of exactly how that looks like, this is a famous Rotterdam breast cancer data set. Well, it's 5 rows of it. It's bigger than that. But so you see the patient ID, age, pre or post menopause, the size of the tumor, grade, nodes. There's some other medical covariates here. And then this is the T variable, the time. And this is, okay, death here, they were all censored. So this person was censored at time after 2,690 days. But if anybody here had died, this would be a 1, and then you would know that that person died after 4,533 days, right? So that's how this is how survival analysis data sets often look like. And now I'll show you. This is if you fit a Kaplan-Meier to that data set, you get this. And in R, by the way, this is literally those 2 lines give you this. So it's kind of very easy to do. And here you're telling it, yeah. Oh, well, I won't go into the details, but so this is for all the patients there in that data set. But say you start stratifying on a certain level of a categorical, right? As I kind of showed you before with the treatments for COVID. So say you stratify on tumor size, okay? Then here you can see, you can at least very easily see that, for example, the people with the smaller tumors, they had a higher survival probability, right? And then the middle ones were in the middle, and the ones without, and this is the tumor size at time 0, by the way. That's an important detail. So you can straight away see kind of certain dependencies in the data, and you can be fairly certain that these probabilities that you're estimating are reasonable. Okay? So which would be hard to do if you essentially if you try to do this with regression in your own way or etc. You end up reinventing this if you want to get it correct. So it's really a good way to do it. You could also look at, for example, another categorical, so premenopausal or postmenopausal, and then you can see that the risk is higher for postmenopausal, for example. And here, if this had all been pre-specified, then you can do a log rank test, which would rule out the null that these were drawn from the same survival function, so you can say they're statistically significant in terms of the differences. Okay. And if I fit a Cox model, never mind most of so you have the standard error and you have the beta. But the one I want to draw your attention to is this one, exp coef. So coef here is the beta. So you can see that menopause, this one is the first level with respect to the 0 level. So postmenopausal has a risk of 1.46. This is a hazard ratio relative to premenopausal. And yeah, you can see, for example, for the largest tumor size, this is relative to the smallest tumor size. It's 3.6. So you can see that here clearly these things are associated, not necessarily causal. That takes extra assumptions and randomization, etc. But these things are associated with higher risks. And just to say last few things in terms of performance. So if you wanted to predict, you're predicting probabilities. So you need to use an appropriate performance measure. This is the C index, and you can compare, for example, this paper from 2017, which compared Cox proportional hazard versus an adapted deep learning model versus random survival forest, which is random forest adapted for survival analysis problems. And you can see that in many problems, for example, the Rotterdam dataset, the performance is not actually that different, right? Except the deep survival model has, I don't know how many parameters and takes, I don't know how much computation to fit. And you can't, well, you're going to struggle to get interpretable things out of it. I can't remember if the authors of that paper actually said much about that or not. But whereas here, I showed you, you have the hazard ratios, which you can kind of interpret easily, and the performance is competitive, not the same, but so it's really something that you should always use as a benchmark if you are doing survival analysis projects. So you'll have to check the proportional hazards assumption that it holds approximately or not. But anyways, there's a lot of things here that I didn't mention. So someone could, for example, go between premenopausal and postmenopausal in that trial. So the X would change value during the trial. One covariate which might induce lower risk at one time might later time induce higher risk. There could be competing risks. People can die from all sorts of causes. The censoring might be informative, and many of these are taken care of in these new techniques called landmarking and joint modeling. And you can Google those just to see if you want to read more about them. Otherwise, for further reading, I can recommend the one on the left, the self-learning text. It's a kind of written in plain English. The one in the middle is a usage guide from world experts in survival analysis. So it's a good one to read if you're going to use survival analysis because it's full of do's and don'ts. And the one on the left, on the right, all the way to the right. I'm sure you're all familiar with it. The first edition did not include survival analysis. The upcoming second edition will. So it's also something that which they've deemed important enough to include. And yeah, last thing, if you're going to do survival analysis, preferably use R. That's the most complete packages and mature are there. But if you want to use if you want to do it in PyTorch and do it in Python, then yeah, that's this personal project which you can submit a pull request to, etc. And yeah, have fun. But yeah, preferably do it in R if you're going to do it. And I think that is it. Thank you.
Thank you, Elon. Thanks for sharing. Very interesting. Also, really cool to see that this technique has been applied to our current COVID pandemic, even with seemingly some good results. But I know you're not an expert there. Let's have a look at the comment section around the questions from the audience. We do have a question from Ahmed. Which is the following. Are you only talking about the linear regression models? What do you think about tree-based regression models like Light GPM? These models are also non-parametric, just like the Kaplan-Meier estimator.
Yeah, so there's in the last table where I showed the benchmark, there's a random survival forest, which is kind of an adaptation here. If you don't want to use, if you think the kind of the proportional hazards and all that is too restrictive. So there are ways of doing that. And yeah, I think that's probably the one I would recommend the most, random survival force. If you're going to look into something more complex than some variation of the Cox model. Yeah.
Okay, cool, thanks. Maybe one more question before we finish off this one. I'm wondering what kind of future developments or future directions do you expect from survival models? Because I think, as you mentioned, the technique has been there for quite some time. It's quite used in industry. And there are some deep learning techniques also coming up. What are your expectations there?
Excellent question. The short answer is I don't know. But there are a number of things where, in a sense, it's such a difficult problem that there are many ways there are many improvements to be made. And landmarking is something that, for example, and joint modeling are things that go some way towards doing that. But the fact that you can have, for example, the covariates changing value, because the Cox model actually assumes that the values are time independent. Whatever that's set to at baseline, so that the menopausal status or the tumor size, that's what it is the whole time. But when you consider the fact that your covariates might be changing over time, and at the same time, the way they impact the outcome might be changing, so the effect, the beta, might also be time dependent. Then landmarking and joint modeling are two ways of addressing that, but it's such a tough problem that it's hard to know kind of, yeah, I think there's probably still a lot of progress to be made there. So I would guess that it's going to go in those directions because it is a very challenging problem for those two things. But and there's also non-informative censoring, but I think those two things, the modeling of time dependence in the covariates and in the effects, I think there's probably more work to be done there.
Okay, good, interesting. I'll keep watching that one. Okay, time-wise, I think we're doing quite perfectly because we have one question left. Question from Kuri. Do you apply survival analysis to detect when the retail default happens if you work for wholesale banking? I don't know if it's something that you can share, but still gonna ask this one.
Okay, yeah, no, I unfortunately can't share that, but it is a tool in our toolbox. Let's put it that way. It's something that we consider when there's a relevant problem that comes along. And I think the main point of my talk is it's definitely something you should consider having in your toolbox, because it will save you a lot of pain and it will get you better results for problems that it fits well for.
Great. Thanks a lot, Elon. Thanks for presentation and answers. Let's move on to the next one.
Yeah, thanks, Vidas. So let's move on to our last speaker for today, Camille de Volk. Camille is a master physics student from the University of Leiden, currently doing his graduation research at INJWBAA, where he's applying his background in theoretical physics to real-world business problems, always using data analytics and modeling techniques. And today, Camille is going to present about simulating the domino effect of defaults. Take it over, Camille, and good luck.
Yes, thank you very much. I see I'm in the show, so I assume everyone is hearing me. Thanks for the introduction, Nicole. So I'm Camille de Valk, and I will talk today about simulating the domino effect of defaults. So there are some things that I will introduce first, and then we'll go into the presentation. So imagine you're working at a firm, and you're doing quite well. You're doing good business. You have some clients and suppliers, and they buy from you, and you buy from them, and everything is fine. So this is a perfect world, and there's no risk from the clients because the clients are also doing fine, and there's no risk from the suppliers. They are also doing fine. So that's all good. But unfortunately, reality is harder than this because the client and the suppliers are also can also have a link, and all of them are part of a bigger financial network. And this is the topic of today, because unfortunately you're not isolated and you have connections. There are more connections than you have only with your neighbors. So your neighbors have all connections, and those have also connections. And in reality, this network is of course much bigger than shown here. What can happen at some point is that while you're doing good business, somewhere in the network someone is not, and this means they maybe go into default. So that means they don't pay an obligation, or at least it means in this context. So we turn them to gray. So we have some gray nodes here. They are in default and they're not paying all their obligations. So their neighbors might also get in trouble now, which might cause them to default. And this might go on for some while, and eventually you are also at risk for this defaulting. So while you were doing good business, because of the network effects, because of the spread of this default, you're also at risk. And what I researched during my graduation project was how this work, how does this effect cascade through the network. The questions are: how many nodes will default? How fast is this defaulting going? And how much flow of money is there still going on? And of course, what's the influence of the network structure in this whole effect? To do this, there are 3 steps essentially to the presentation. First, we need to construct a financial network to run this simulation on. Then we need to actually run the simulation and interpret the results. That's the last step, of course. So let's dive into it. If there are any questions during the presentation, please post them in the comments, and I will be happy to answer them after the presentation. So how do we construct a financial network? We do this with transactions between companies. As mentioned, I'm doing the graduation research at ING at the moment, so we can observe transactions. And for this research, we use the transactions of 2019, and we place a link between two companies, with the weight of the link being the sum of the transactions of 2019. Because we can only observe Dutch ING networks, Dutch ING companies, Dutch ING accounts, there may be a lot going on that we don't observe. So just to be sure that we have a fixed network, a closed system, we filter the exogenous forces, so the private individuals, the foreign accounts, public administrations, financial institutions, and non-ING accounts. So public administrations and financial institutions, we could observe them, though they would not behave in a similar way to the companies because they will not default in a similar way. This will result in a closed system with a fixed number of links and a fixed number of nodes, and we will enforce conservation of money. And this is a controlled approximation. Of course, it's not the actual transaction network. I think there's no one that can actually observe this or model this. But given that ING is the largest bank of the Netherlands, we can say that we observe most of the transactions. So this financial network actually is quite large and is close to reality, at least for the Dutch interfirm network. The second step is to simulate the actual domino effect of these defaulting companies. So how do we do this? We run some iterations of an algorithm, the fictitious default algorithm, and it looks like this. For every node, you observe the incoming money and you observe its obligations. And if you have more incoming than obligations, you just pay them, and you save the excess money to your reserves, your profit, so to speak. And in an ideal world, for every node, this would be the case, but unfortunately, that's not the case. So there are some nodes that will be in default by definition. So if you have less incoming than obligations, you are in default. But you may have some incoming money, and this incoming money, you can spend it to other companies. You pay this according to a certain strategy, which I will come to in a bit. Every stage, you record the number of defaults and the total flow of money in the network, and you run this over and over. And when there are no more changes, you terminate. In reality, this can go on for more than 10,000 iterations. And remember, one iteration for us was 1 year, 2019. So that would mean we would look 10,000 years into the future. So to keep it a bit real, we stopped the simulation at 1,000 iterations. So these strategies, what are they? How can you still pay money if you are in default? There are 3 strategies that we implemented. So the first one is to divide your money equally. This actually comes from the literature on cascading defaults from about 20 years ago. So when you have less money incoming than outgoing, you divide your money equally over your creditors, and you do this proportionally to the obligations. So if you have 50% incoming, you pay your obligations 50%. The main motivation for this is that it's quite easy for calculations. This will become a matrix multiplication, which you can run analytically. And this is what was done 20 years ago in literature. A strategy that's more motivated by observed behavior from colleagues at ING is largest creditor lost, where you pay what you can, but you do this in such an order that you pay your largest creditor last and your second largest creditor second last. So you pay the small bills until you run out of money. The motivation for this is that you have less creditors to deal with. Only a few large obligations that you don't pay. And for the simulation, this wouldn't matter, but in reality, this would mean you would have to ask less people for later payments. And you can also do this the other way around. So you pay your largest creditor first so that you get rid of the large bills, and these small bills, you hope everything will be fine about them. So you won't have any big bills lying around. And there's one more flavor to choose. When you cannot pay a bill, so for the largest creditor last or first, so you stack these bills. The last bill you may not be able to pay, you can choose between only pay this bill when you can, so you save some money in your reserves until you can pay this bill, and then you pay the bill, and then you do this again. Or you always pay whatever you can. So if your last bill that you would pay is 1,000 euros, but you don't have 1,000 euros, you have 500 euros, you pay this 500, which is not enough, but it's something that's the idea behind this. So we observe the total flow of money in the network and see how what's the difference between these strategies, and this looks like this. As you can see, most of them tend to zero quite quickly, so I will show this on a log plot. So it's the same information as just now, but on a log scale. What we see here is the total flow of money compared to the available money flowing in the network, where the colors are the different strategies. There are some things that we can observe. For example, the red and the orange line, so that's only pay in full strategies. Those lines are not only decreasing, they have some oscillations going on. And this is due to the fact that you can save up some money before you pay a bill, and then you can pay the bill, and then you do again this saving up, which will lead sometimes in higher flow and sometimes in lower flow. The trend overall for all the strategies is decreasing, and also for the lines with the oscillation. Another point is that the difference between the largest creditor last and largest creditor first is quite big. So remember, this is a log scale, so this is orders of magnitude. And And the question now is, why is this the case? Why is largest creditor last smaller than largest creditor first in terms of total flow? And maybe you can think about this already a bit, because everyone is paying their largest bill first or their or last. So this, of course, will result in a different flow. So how does this work? When we look at the payments that are done in the last iteration, it will give a sense of which bills are paid and which bills are defaulted on. So for the orange and the blue line we just saw, the largest creditor last, we see that overall the most obligations that are still paid are on the order of 500 euros, so to speak. The area under this distribution is the total flow of money we saw in the last slide, so the height of the line. For the other strategies, the largest creditor first, we see that this distribution looks definitely different, because it's lower, but it's also more skewed to the right. And remember, this is on a log scale, so a bit to the right, so a few steps to the right can already mean thousands or maybe millions of euros more or less. So we see indeed that the area under the distribution is much higher for largest creditor first because of this log scale. So how does this compare to the obligations that had to be paid in the beginning of the simulation? I plotted them in purple. So these are not payments, but these are obligations that would have to be paid in the beginning of the simulation. And indeed, you see that for the largest creditor last case, the small payments are fulfilled, and for the largest creditor first case, the large payments are fulfilled. And this is why the difference in the flow is this is where the difference in flow comes from. So how do we interpret this? What does this mean? Where does this come from? This effect of decreasing flow. For this, we use a technique where we model the network. So as I mentioned in the beginning, we are trying to investigate what the effect of the network structure is on this cascade of defaults. You can model networks in various ways, in a variety of ways. But for our purpose, we use a technique which tries to replicate a certain property of the network. And the property that we are trying to conserve in the random network is the strength. So this is the total flow of money through a certain node. I plotted here the out strength of the ING network. The plot for the in strength is similar to this. And you can construct a random network that has similar properties. So you can do this in two ways. I plotted them both. So you see at a first glance that the strength distribution is fairly similar, which is what the random network model is trying to do. And the orange random network model, it not only tries to conserve the strengths, but also the connections between sectors. So you can imagine a bakery, for example. It may have a certain strength and it might connect in the random network to other nodes, but a bakery will almost certainly have a connection to a farmer, and not to steel factories, for example. So you want to keep this information in the model, and that's in the orange model, the sector model, which distinguishes 737 sectors. The green model doesn't take these sectors into account. It just takes the total flow per node into account. And what we're trying to do now is we do the simulation not on the empirical network that we observe, but on the random network. And if the behavior that we observe is similar, then this effect of cascading defaults is explained by the properties of the random network, and therefore you could say that it's explained by the properties that you've constrained. When this is not the case, you can argue it the other way around. So let's look at the results. You already saw this picture, but there are more lines coming into this plot, which would make it a bit chaotic. So I plotted this in a different way, where I took the height of the the line in the last few iterations and plotted it on a bar chart. So that looks like this. There are coming more bars in this picture. So on the left, we have the empirical. We already saw this, the relative eventual size of the economy, the height of the bars. For the random networks without sector information, it looks like this. And with the sector information, it looks like this. So you can distinguish them with the hatches in the bars. There are already some things that we can see. For example, the general shape of the height of the bars, which might tell a bit how the strategies compare to each other, is similar for the empirical network and the networks where the sectors are, the random networks where the sectors are constrained. And the factor is between the bars is approximately 21%. It differs a bit. Note the log scale, by the way. That's why this is 21%. There's another observable that we can plot, which is the number of companies that did not default. So the more companies that did not default, the higher the bar and the better for the economy. So for the empirical, it looks like this. For the random networks without sector information, it's like this. And for when you replicate the sectors, it looks like this. Contrary to the relative eventual size of the economy, in this measure, so the number of not defaulted nodes, there is almost no difference between the height of the bars for pay what you can or only pay in full. So you see that there's a difference between these bars, and it's also present in the sector model, but this is not present in the number of defaulted nodes. Furthermore, there's also again the shape of this of these bars is replicated for the models where you replicate the sectors and not where you exclude the sector information. There, the number of not defaulted nodes is approximately the same. Before we draw our conclusion, we have to reiterate maybe what the assumptions were that we made we have to reiterate this. So the assumption that we made is that the obligations between the nodes in the network are constant in time, which is which may be the case, but as I mentioned, these iterations go on for 1,000 iterations, so that would mean thousands of years where the financial network is constant. Maybe you would want companies that make a profit to gain more connections, or maybe to gain to get a higher weight of the link between companies, or maybe a lower weight when the company is making a loss. You could change these obligations in time. Also, the exogenous cash flow is not considered, which might pose a threat to companies which maybe are not in danger at all. So the simulation there might improve. So there's some filtering done, which would mean that companies that are dependent on private individuals, for example, restaurants, given this simulation, they would be at risk, but maybe that's not the case at all. The same goes for companies with in sectors which are dependent on international trade, or all these other filtering points. To conclude, the difference between these strategies is as follows. So for the largest creditor first, we observe a higher flow, but there are fewer surviving companies. The higher flow is due to the fact that that people pay their large creditor first, by definition, and this happens more often than in large creditor last, which is hypothesized that this is the actual behavior of companies. But there are more surviving companies, which may be a good thing. But in general, this simulation can be improved a lot. And there's another very important conclusion, and that's when you have these random networks that preserve the flow between the sectors, the cascading default simulations results are better than when you don't conserve the flows between sectors, as is the case for the other model. And with that, I want to conclude and maybe show again our company, which was at risk or not at risk. So it matters for this company where in the financial network it is and who are the neighbors. And that's what we've shown in this presentation on cascading defaults, simulating the domino effect of defaults. If there are any questions, please ask them in the comments, and I'm happy to answer them.
Thanks, Camille. Very, very interesting. Very impressive results. Wow.
Thanks.
We still have quite a bit of time. So if you're wondering whether to ask a question, go ahead and ask it in the comment section. We have one question coming in already from Claudia. Oh, hey, Claudia. Why have you decided to use a step size of 1 year for simulating your model? Wouldn't it make more sense to use a more granular step, say 1 month or even a week?
Yeah, that's a good question. Thanks. The reason behind this is that you try to get a network of obligations, so bills that actually have to be paid. So not transactions, but you try to go from transactions to obligations. And when you would do this in a step size of 1 week, that would mean, for example, all the obligations that happen, all the transactions that happen at the end of the month, every month, those will be neglected. And why not a step size of 1 month? Because if you do 1 month, you might have some seasonality in there that you want to exclude. So if you have just 1 year, you discard all this seasonality because you sum over the entire year.
Oh, makes sense. Thanks. See a question from Alina. I had the same question looking at the talk as well, to be honest. What practical uses would you say are possible there? Maybe also, what kind of advice or you could give to companies or to policymakers, knowing what we know now, running this after running the simulation?
Yeah, that's a good question. Thanks. So a lot of risk models at the moment, they look at the company on its own. But then when this simulation that we're doing improves and it gets more realistic and more information is in the simulation, you might be able to estimate risk from the network itself, so systemic risk, and not only for the company but also for the neighbors of the company or the neighbors' neighbors. So when you would observe that some company 3 steps away would be at risk, this might pose a threat to you, which you wouldn't be able to observe without this simulation. So it would give a more realistic risk estimation given the financial network on its own.
Okay. Thank you. I see we also have a bit of a different question. Maybe it's best to answer it offline around how to learn new topics in educate and data science. To stay on the topic a bit, I would ask you another question, now a bit more on technical side. What kind of other ways have you thought or would you see to model these cascading default effects, and why did you go for the agent modeling approach?
So the honest answer is because I'm doing the research from a physics perspective, and I'm doing this simulation agent based. So that was the research project on its own. So other ways of simulating this would actually maybe look at actual defaults, which I'm not doing at the moment. I saw a question about that. I will maybe come to that in a bit. So that would be another option. So to look for defaults and see what caused these defaults, and then try to maybe train a classifier on that, or time to event analysis, as we just talked about. Yeah, so the actual defaults, I saw a question about that, if I may answer that.
Go ahead.
So there was a paper some years ago, 2-3 years ago, that happened in Japan, which used a similar simulation as I did. In the simulation, they also did this cascading defaults, and they recorded actual bankruptcies of companies. So not defaults, but bankruptcies, which is one step further. And they observed that given a place in the simulation, so for example, in which stage they default, there is a correlation to actual bankruptcies. So it's not the case that when you default in this simulation, you actually have a bankruptcy. That's not one-to-one, but the probability increases. So this has a predictive. This can be predictive in that sense. So that's also very useful.
Oh, cool. Thanks. So quite a few other promising research areas I see there. Okay. Let's look at the rest of the questions. See quite a few coming in. Oh, one from Steven. Hi. What kind of tooling did you use to build up and run algorithms on these networks?
I'm not sure I understand the question, but I think you're asking like what programming and what
I suppose so. Yeah.
Yeah. So I used Python for this. And the simulation, actually, I had to learn a new programming language, which was Cython, which is C and Python, which is a Python interface for, or C interface for Python, because this you saw the numbers on the network. So the network is order 10 to the 6th number of links, and 10 to the 5th or nodes in the network. So the simulation is quite heavy. So I reached out to Cython for that, to do this simulation quickly and efficiently.
How long did it take to run it in the end?
Well, one simulation of maybe 1,000 iterations was 10 minutes or so.
1,000 years in 10 minutes.
Yeah.
Not bad, not bad. Okay, I think also another challenging question. Did you measure how reasonable were your assumptions?
Well, no, that's a good point. No, I didn't do that much, but that's one of the next steps of this research, definitely. So my supervisor from WBAA, the next steps will be to get more economists on board, to make these assumptions more reasonable, because we already spoke with some people from credit risk. For example, the defaulting strategies that we have, so largest creditor first and last. One of the other things they suggested is pay your critical creditors first. So your utilities or your production companies, pay them first and then the rest. So that's maybe a strategy that you could try to implement in order to get a more economic simulation there.
Okay, thanks. Let's move on. I think the default one tackled. Fritz also saying you could use Gaussian Coppola models as an alternative. Also, question from Ajax. A lot of network-based optimization of multi-agent behavior, we see that there is often an added value to have central authority. Is this something that could be simulated as a strategy? As in, a bank would suggest to its client which credit to pay back first in order to optimize the network to reduce defaults.
Yeah, we experimented a bit with this.
Nice.
Though it's not it wasn't implemented in full, but we implemented the strategy we called Robin Hood. So not only the size of the obligations we're giving to the nodes, but also the equity of each of the nodes. So how bad they were in default at the moment, and they would pay the companies first that were that had the lowest equity. So this would be your central authority, saying you should pay this bill first because this company is in trouble at the moment. And you indeed saw that the total flow was higher than for the other strategies. Though this is some time ago, and the whole framework changed a bit, so I did not include it in the final presentation. But yes, this would be definitely interesting, because it might help for the total flow and the defaulting companies. Yeah,
definitely would be interesting to follow up. Okay, I think we're doing perfectly on time. Let's thanks a lot, Camille, for a great presentation and interesting discussion. Let's close it off.
Yes, I think we can call it a day. We would like to thank our speakers for their interesting talks. Our after-event material will arrive soon at your inbox if you have registered. Also, many thanks to the team behind the Data Science and Data Engineering Meetup series. So Zeynep, Jesse, Daniela, Feijuan, everyone. Our next Data Science Meetup will take place on the 9th of December and the Data Engineering Meetup on the 21st of September, so stay tuned. It was a great pleasure co-hosting with you today, Vidas.
It was a pleasure for me as well, and see you at the next one.
See you at the next one. Bye.